let's try to do something different today. I want to go over whether we can, whether we understand different properties of the bag of words kind of features and vectors we produce them, opposed to word embeddings that we have learned about last time. So if you can, using your laptop or your phone, you can either go to see that link at the top, you will need to manually write it, or you can use the QR code, I believe. Can you try this for me? I'm honestly not sure whether this is gonna work. I have been setting up this in like last 10 minutes. I don't like that it shows the what's going on with your answers live, because then that kind of biases you towards the other answers. But let's see. All right, I won't give you a ton of time for this because we have almost 10 of these to do. So the first question is about whether these count features or bag of words, what's their length? And I have seen a few short ones showing up and then disappearing. Most of you, at least so far, have said that these are long vectors, and that is the right answer. It's long because these vectors are the size of the vocabulary. Try to mentally imagine how many English words there are in a lexicon. That's a lot of words, right? So if we work with a very large corpus, remember, corpus is a collection of written text. What we would end up is vectors of at least size of few dozen thousands. And those are really long vectors, right? Now, let me go back to these things I have prepared. If we can do the same thing if I ask you the same questions for average embedding, meaning I have some input text, I have tokenized it, I use the average embedding, what your answer would be then? Okay. Oops, right. Okay, so here, most of you think that average embeddings are short, and while this is easier to answer relative to what, if we compare them to these features such as count features such as bag of word vectors, then average embedding is really short. So the average embedding is going to be of the size, if we work with word to vector, of 50 or 300, which is way smaller than, let's say, 30,000, which is the typical size of the vocabulary. So in that sense, average embedding is much shorter vector than the bag of words feature. Next question is whether the count feature vector, bag of words, is interpretable. What's happening with no? It's decreasing. How can I? Instructions. Oh, yeah, nice. Okay, you can't then see responses. Brian, you comments. All right. Let's say you are done with that. So your responses are mostly yes, with few no's. Would any of you like to explain their decision here? Okay, excuse me, yeah.
I said yes, because I'm assuming interpretable in this context means you can understand the matrix if you're looking at it. And if it's a count feature vector bag of words, that just means that each point is just how many times that word appears. So it should be interpretable by you.
Exactly, with few corrections, just to be slightly precise, your log is good. But vector in itself is something we would refer to a point in a vector space, and each dimension of this vector kind of represents almost like the coordinates in the vector space. So yes, you are right that each dimension in a feature vector, if we are talking about bag of words, is a count, a presence, or TF-IDF of a word in the vocabulary with respect to a document we are representing with this feature vector. So it's interpretable. If we know this dimension means if it's like 1 and it corresponds to word dog, we know that, this feature means that the word dog was present in the document. Okay, so now, if I ask you the same question with average embedding. So if I take word embeddings of words that are the given input, and then I average their word embeddings, is the corresponding embedding interpretable? Do I know what each dimension of this vector means? If you haven't seen or you came late, you can answer. There is a link at the top, and then you can use QR code as well. All right, let's see your responses. Okay, so we have many of you saying, guys, come on. This is so funny. Yeah, so most of you have said no. Would anyone like to explain why not? Someone who hasn't answered the question yet? Yes, please. Sorry, guys. I don't see you. Feel free to shout.
Yeah, no worries. When you're doing this average embedding, you're essentially taking multiple representations of a word and sort of just, putting them all together. And because the dimensions don't correspond necessarily to the existence or lack thereof of a word in this sentence, you can't really tell. All the information is just kind of put together.
Exactly, right. There are two levels to this answer. One is that the word embeddings themselves that we start with are no longer interpretable, meaning we have no idea what each dimension actually means, because we have learned these embeddings through the data, right? Like we have collected a bunch of unwritten text, and then we have learned using the skip up algorithm that every embedding, we have iteratively changed it such that we are better at predicting whether a pair of words appear together in the corpus or not, right? So everything was done through learning, and we haven't really imposed what those dimensions should be. So now they can be whatever they want to be. And these dimensions, though, will be useful for the task of predicting whether two words appear together. And because this is realization of the distributional hypothesis, we have ended up with embeddings that when they have similar meanings, they tend to be closer in the vector space. Okay, so later on, if you read more about this, you will learn that there are interpretability works that examine geometry of these vector spaces, and you learn more about what these vectors represent. But on their own, you can't really tell that dimension 10 means something without further inspection. Okay, now let's move to the next question, which is, are these bag of words vectors sparse? Meaning, do they have a lot of zeros? Okay, so here most of you say they are sparse. And they are sparse because, as we have just said, we are recording the present absence counts of words in a given document, but our vocabulary is much larger than the number of words that actually appear in a given document. Therefore, most of the dimensions are going to be zeros. How about average embeddings? Are they mostly sparse? Or are they what we call dense, which would mean that they have no zeros? Okay. So again, opposed to this bag of words vectors, our average embedding is not going to be sparse. Actually, it will have no zeros whatsoever. There is going to be always some small number there, not necessarily small, but I want to say like instead of having like a 0, 0, if we have a small number close to the 0, it's possible, but not really 0. And this is nice. We won't go into this, but if you take a deep learning course, you might learn more about this. Neural networks simply don't work easily well with sparse vectors. So achieving sparsity in neural networks and training them and then scaling them is a really hard problem. So with neural networks, you want to have something that's, we say, dense, that doesn't have zeros in the input. Let's see what the next question is. Okay, so the next question is, do bag of words regard word order? So that means whether, I'll give you an actual example. So here, I mean, I'm kind of answering this, but it wasn't terrible. In fact, it was great. And it wasn't great. In fact, it was terrible. Are two sentences which have exact same words, but they are put in different places. Just a second, let me see what the general response here is. Oh, I didn't activate. That's maybe what you're trying to tell me. Okay, so general consensus here is that no, they disregard the word order. Does anyone want to say why?
Well, I have a question.
Okay,
If
yeah.
we did a bag of words with an engram, would it then do word order?
Yes, that's a great point. So with engrams, we are to some extent capturing order of the words bounded by the engram size, right? So if I don't know, I use negation like word not, and then if that's captured within the context of an engram, such as if I choose Python, then yes. But if it's more, you know, it kind of goes outside of the bounds, then I wouldn't. So sometimes yes, sometimes no, depends on the size, right? But in general, a lot of times, especially bag of words definitely disregards the order because we just don't care in which order words appear. We simply take their positions, we take their, counts, right? So where they appeared in the sentence is completely ignored. How about average embedding? Do we consider the order of words when we average word embeddings? Okay. All right. So here we have not a super clear consensus. And it's still lower. Okay. So I would love to hear. Let's hear this less popular opinion that average embedding does take care of the word order. I don't want to put anyone on the spot, but I hope you feel comfortable maybe sharing why they think that is. Yeah,
I said it does regard word order in a sense because some words only come before use, right? So if you're getting like the average of embeddings and you have a list of like example sentences that keep on saying not good, wouldn't it then when you're training your model, it would give your embedding more negative sense for good just because not is constantly in front of not in front of good.
okay, but how does this information about not appearing before other word comes into a play? Because imagine I write my code in this way. I tokenize my sentence, I represent each word with its word embedded. And then for no reason whatsoever, I decide I'm going to scramble this order of the word embeddings and then average them. Would I get different vector than if I didn't do this reshuffling from word embedding? What is it? Yeah, like, so just to kind of go to visually show, so great movie. So that's my sentence. Imagine I tokenize them like this. I have a word embedding for each one of these, right? And I average them. So I have 1/3 and then average of these embeddings, right? If I have shuffled these vectors and then average them, I will get the same average regardless of the shuffle, right? So now we're here, we are taking into account that great had appeared between movie and other way around. So here again, the average embedding won't care about the word order. Yeah.
I thought the word embeddings took, when the embedding was created, it takes into consideration the nearest neighbors to that word. It considers this word in context to, let's say the two words that come before it and the two words that come after it. So by shuffling, wouldn't that then change the value of those embeddings?
Okay, so first of all, we are talking about this representation and its properties, right? So we are not talking about the model that have produced them, but I see a connection between, does the information about the context now leak into the embedding itself? And it doesn't, because again, when you train the word-to-web with skip-gram algorithm, you have taken the one word that appears in the context, but again, you forgot where exactly has it appeared, right? Like it could have appeared before and it could appear after. And again, I don't think the position itself is important for the word-to-vec algorithm to learn whether two words appear together. So let me try to make sense of this. You're just predicting whether two words can appear in similar contexts. But now think about their relative order is important to say that. Okay?
So it's embedding in context to other words, but it's more of a general context rather than, this word appears before and this word appears after. Instead, it's just these words will appear close to one another.
Yeah. So for example, if I give you two words and I ask you, hey, can you imagine these two words appear together in a small window? You wouldn't really think about, like, you would think, not appears together with the adjective because then I can, introduce the negation, right? So you're kind of thinking about the larger linguistic phenomenon. You are not thinking about, this word will appear before this word or after this word or anything about that.
So their proximity is being recorded, but not necessarily their order. Is that correct?
I would say so, yeah.
Okay.
Yeah. And then again, you have no idea, you have in your word-to-vec skip-gram algorithm, in no way you impose that one word appears before the other. So your context word that actually appears in the window can appear before or after. It can appear 2 position before, 2 position after, but we have completely broke that relation when we have built our positive pair. When we build our positive pair, we just say, oh, these 2 things appear together.
Okay.
Right, but we didn't record how exactly it appears together.
Okay, okay, that makes sense.
Yeah.
That has to do with the distribution hypothesis, correct? It's saying that we can determine the meaning of a word based on in aggregate, the words that appear near it.
I want to say aggregate, that seems like addition. You have said everything right up to that point. So distributional hypothesis says that words that appear in similar contexts tend to have similar meanings. So in skip ground, we realize this assumption by trying to find embeddings such that from them we can predict when 2 words appear together in the context. And if they are close to each other in vector space, then we can make that prediction. But with skipgram itself, we are not averaging anything. So again, don't forget what I showed you the last time. Last time I said, and I started the lecture, don't conflate these 2 models. So we have model 1, which creates word embeddings. From it, I get my embedding matrix. And once I get my embedding matrix, I forget about the model. I delete it. I don't care. And then when I create my model 2, which is my classification feed-forward neural network, this embedding matrix becomes its first layer, layer 1. Okay, from which I do the lookup, I find my vectors, retrieve them, and then I average them. So just because we use averaging here, don't mix it with the first model we have created. Okay, we have 2 more questions. I'll go quickly through them. So first one is whether the bag of words vector capture the notions of synonyms, antonyms, similarity, relatedness, all these semantic phenomena that we care about. Okay, so general consensus here is no, and that's right. This is how we motivated word embeddings. If we have synonyms, they are completely different words in the vocab. And because the bag of words cares just about the surface form of the words, it's going to add them in completely different dimensions. And then similar for antonyms, although they will be captured by different dimensions, in no way it will signal, well, you have exact opposite meaning, and similarity and relatedness will not be captured. How about word average embedding? Okay, so here we have maybe not as clear of the consensus, but generally you are saying that, yeah, we will capture synonyms, antonyms, and this other linguistic phenomena. And that would be right. I would agree with that. So remember that with average embedding, we are going to get these synonyms and something that's related or similar. They are going to all be closer in the vector space because that's how we produce these embeddings. Unlike a bag of words. Okay, so these are all the kind of questions I wanted to ask you. I think you kind of get the general theme and properties of these 2 feature representations. So this is really important to understand these differences. So if some of these things didn't land, try to please go over it once more on your own. But knowing these differences is really important bit in this course. Okay, so now I'm going to continue with some analysis of these embeddings, and then we are going to completely switch gears, and I will kind of go over how and why, and then we are going to go into, time permitting, into a whole new, I would say, section of this course, moving away from this classification stuff. Any questions before I move forward? All right. So in general, in NLP, we have two kinds of evaluations. One is so-called intrinsic, and the other one is extrinsic. And most of the time, we care about extrinsic evaluation. So in extrinsic evaluation of word embeddings, we can go back to this idea that we have created two models here. One is the model that gives us the embedding matrix, and the other model that actually is doing the classification, and the produced embedding matrix is its first layer. So in extrinsic evaluation of word2vec, you want to see that adding these newly learned embeddings improves the performance on your downstream task, which is in our case classification. Okay, so here, basically the way you would go about showing the benefit of your word embeddings would be to have two runs of your feed-forward neural network. One is with randomly initialized embeddings. And another run with your word2vec or whatever other embeddings you would like. So I will call them pre-trained word embeddings. Okay, so you have two runs, run 1 and run 2, you train them. And what you want to see is that the performance, such as accuracy of run 2, is larger, notably larger than accuracy of run 1. And here we would use evaluation set. So this is a downstream or extrinsic evaluation of our word embeddings. We have produced them because we believe that they are better representation of words, and we want to show that that's indeed the case. You might say, well, couldn't I use the bag of words vectors here to show that? And I would tell, although that's seemingly a good idea, the issue is that we know that due to sparsity, you can't make this neural network work. So you would need to compare it to randomly initialized one. But you can have another model. We would call this a baseline. So, and this is basically when I started my PhD, this is what we would do a lot. So your baseline would be some previously best model, say state-of-the-art model. And that would be something like support vector machine with manual features. And manual features, we are referring to features that we define, such as presence or absence of words in the vocab or their counts. So maybe this was the state-of-the-art model. And again, you want to see that the accuracy of my run 2 is much better than my baseline. And this is how machine learning research very often works. We say, okay, if I do this development, it should cause my performance to improve significantly. All right, then intrinsic evaluation is basically testing whether the actual task that our model, skip-ram model, is designed for is good. So here, specifically, we would use similarity. We would take the word embeddings of two words, and we would check their cosine similarity. And then we, for many such pairs, we would see whether our scores, our cosine scores, correlate with human judgments of whether these two words are similar and how much. So you would have here, imagine I have pairs of words. So word 1 and word 2 can be word 1 and some other word, or word 2 and word 3, 2 and 3. And imagine you have asked some people, hey, can you give me on scale to 0 to 1? Tell me how similar these words are. So maybe they say 0.6, 0.1, 0.23. And then we would also use a cosine similarity coming from our word embeddings. And we get some numbers 0.7, 0.2, 0.3. So they're not exactly the same. That doesn't matter. It's important that they are correlated. You can see that here high similarity by person is kind of associated with high cosine similarity and so on. So if these two, if you imagine you have two rows, two columns of numbers, if the correlation is high, we would say, oh, this vector model is good. Typically, again, we have baselines here. So maybe in 2014, word2vec was released, and then I told you we won't go over this, but many other word embeddings were proposed. Then they can also measure how their correlation of their cosine similarity produced by their word embeddings is. And then if they achieve higher correlation, then they can say we have a better vector model. Okay, so here I want you to remember that in general, in NLP, there is extrinsic and intrinsic evaluation. And specifically for word embeddings, that means what I have just described. Okay, now I'll go over various things just quickly. First thing is that very often you'll see word embeddings being visualized. Remember, these are high dimensional vectors of size, let's say 300. And you can't visualize in a 300 dimensional space directly. So you would typically use some dimensionality reduction techniques to plot these in a 2D space. I do want to warn you, if you are taking data mining, you might learn more about how these kind of dimensionality reduction techniques and their visualizations can be finicky and deceptive. So just keep in mind that these aren't perfect visualizations, so they can come with issues. I highly recommend this blog post that shows how by tweaking different hyperparameters of these visualization techniques, you can get widely different visualization. And then depending on which visualization you're looking at, you might have widely different conclusions. But very often you'll see something like this. And here, I believe they are taking to represent two bigrams, like not good. They are taking the average of not and good. I mean, they're embeddings. And you can see here how you are getting these clusters of semantically related phrases, which are not exact synonyms, right? So you have not good, incredibly bad, dislike, bad, worst, right? So this is kind of connected to that similarity / relatedness concept. And similarly for, more positive phrases. But then here you have grammatically related words that have similar function in language, such as pronouns or prepositions and so on. Okay, another thing you might see very often is this analogy or relational similarity. So it's almost a sin that I didn't mention the queen-king example when I introduced word embeddings, but I did this intentionally because I do believe this is sometimes blown out of proportions. Here I linked a paper that talks about many problems of analogical reasoning with word vectors. But nevertheless, so the idea is that these word embeddings, they have special geometry if we start to look into the geometry of these word vector spaces. And sometimes, not so often, which is the point of this paper, sometimes they will, by doing the arithmetic with these word vectors, you will capture some aspects of meaning. So there are these analogy problems in psychology where you try to predict A is to B as A star is to what? And then you need to answer this question. So here you have most common examples you will see here that king is to man as woman is to what? Does anyone know the answer? Queen. Yeah, and here we have apple is to tree, what grape is to wine. And then you have various examples of this, and we as people can figure what B star is. And what this analogy works with word embeddings are trying to do, they're trying to see whether if I add a vector of, basically, if I take B and subtract A and add A star, and then get some vector and look at the nearest neighbor, do I get the answer to this analogy problem? So basically saying A is to B as A star is to what is similar to vector of B minus vector of A plus vector of A star should give me the answer to this question. And interestingly, sometimes that happens, and that's very cool to show. Again, I want to warn you that there are many exceptions where this does not happen. So while it's a cool example, and there is something to the geometry of this word embedding vector spaces, it's not always the case. And many times it isn't that you can't solve analogy problems with this vector operations. This gets kind of regain attention again because I will just quickly mention this. If you take my interpretability course next semester, you can learn a ton about this. But these days we are trying to find some more interpretable replacement models for our best neural architectures that we are going to learn very soon about, and for large language models. And then something very similar called the linear representation hypothesis is also kind of suggesting something like this. So this has, again, regained some attention. So I'll keep it pretty vague, but then if you're interested in more, hearing more about all of this, then definitely take my interpretability course next semester. Okay, and then last thing I want to say about analysis of these word embeddings is that people have also studied various societal biases related to this. So you can take the same notion of analogy and apply it to these social biases, and people have tried that. So they would do vector embedding of computer programmer minus vector of man plus vector of woman, and then they would find that the vector of homemaker was the closest one. Or vector of doctor, subtract vector of man, add vector of woman, and you would get the vector of nurse. And the idea here is that through these analogies, these researchers have shown that these typical societal biases have been encoded into these word embeddings. Now, why is that a big issue? So imagine I am, and this has actually happened when Amazon had trained a classifier for resumes, and their resumes have rejected every single woman in the pipeline. And then they could go back and kind of tie this to this word embedding. So if your word embedding is such that it never associates being a programmer with being a woman, then it will use these patterns to predict what's a suitable candidate, right? We're going back to our classifier. In the end, is looking patterns in the input, which are now features of word embeddings, and associate them with the output. So if I have built this model and it's using this, what we call shortcuts, I would never get qualified female programmer in my hiring pipeline, which is obviously bad. And this is called allocation harm, when you are not giving resources, namely jobs, to the certain demographics, not because they are not qualified, just because you have a biased classifier to start with. For me personally, this next problem is really interesting. So we learn these word embeddings through data, and this data, because history is the way the history is going to reflect these societal biases because they just simply exist in the world, right? So we will have a lot of mentions of women being nurses or men being programmers, and this is where the model captures these associations. Now, there is something called bias amplification, and that means that, let's say I have seen pair of words, woman and nurse, 10 times in my training data set. if I was later to build a language model like ChatGPT, is going to, with much higher rate, generate women with nurses, meaning is going to amplify that frequency. You have seen these two entities together in the data. And this is called bias amplification. Basically, gender terms become more gendered in embedding spaces that were in the input text statistics. And one paper I've cited here is one of my favorite papers that has done and explored this for image classification. And one insight that's really starting there is that they have tried to remove so many things from images that it would be impossible to tell what the gender of a person in the image is, like completely deleting the person from the image. But then things like a salad in the background would leak what the gender was, because there are so many images of women in kitchen with salads in the background. So it's a really hard problem to stop models to using these patterns that have been very successful for them to do the end task. And then we have a final problem of representational harm, where we build these systems that demean or even ignore some social groups. So in this paper by Zhu et al., they have found that certain names which are associated with certain demographics, I believe in their paper, names that are typically given to Black people have been in the vector space associated with what would they call more unpleasant words. So there is nothing, of course, unpleasant about those names, but because the data is just so messy and noisy, the models have learned these similarities between certain demographics and names that are typically given in these ethnicities together with unpleasant words, which can then lead to systems that completely ignore and demean these social groups. So for example, first versions of GPT-3, you can follow that space in 2020, no matter how hard you try, would not stop generating something about bombing if your prompt included the word Muslim in it. So you can write the most beautiful story about a Muslim person, and it will still continue generating something about bombing. And this is exactly this representational harm that we're talking about. And finally, you might think, okay, how about we fix these word embeddings? How about we just clean them up and remove that information? This is something people have been trying, but it is incredibly hard problem to debias these word embeddings. So I guess I'm finishing on a very negative note, but I want to say it's really important for you to know where these biases can creep in. And then there are other techniques to kind of watch out for whether your, let's say, classification system is doing something that, you know, you have fairness metrics that you can use and that you should be using. Once we start to talk about LLMs, we are going to come to a phase called reinforcement learning from human feedback. And this is a stage where models are trained to stop explicitly saying hate speech and harmful or illegal stuff. So these days, it's much harder to have something like ChatGPT produce something that is outright hateful. But these kinds of biases are still present. So you will see newly works released in 2025 that show that, again, no matter how much you try to prompt the model, maybe you want to use it for creative writing. If you have, let's say, non-binary persona, the model will always default to some kind of stereotypical notions of this person. So they're always going to be an activist and be doing stuff that stereotypically would be the case, and it would be very hard to write something creatively about these entities. Okay, so we are going to talk more about this, but yeah, this is really important to know. Any questions about this? Sorry, yeah.
That I think it's like really hard. But I wonder, if we have a data that's extremely neutral and we train it on a model, would it still use the biases that it had from, like, let's say, a previous set of data on this new set?
Yeah, I think I don't know the answer to your question because I don't think I have seen something in like neutral data, like what that would, right? Because it's not just about something that's explicitly associated. Give this example I have given you with like salads or babies in the background, or even like put people out of the equation and something like grass, like certain animals are always in grassy areas. Models will always look into these subtle subtle stereotypes, subtle biases. So it's really hard to produce data that's both realistic and what you would say neutral. So I don't think we have answer to the question because I don't think anyone had produced neutral data where these kinds of biases are coming from.
And then add on to that, I've heard about this like new thing called like subliminal learning.
Oh,
It's like
sorry, second.
subliminal learning.
Okay.
Where it's like if you try to like train a model on synthetic data.
Mhm.
And it had these like biases in it before, it would like take those biases and it would learn those biases in the new model. So like, for example, it's like if you taught like a model to like really love like an eagle or whatever, like, and you try to train the model even on like no mentions of eagles, it would still transfer that like, or like liking the eagles. So I guess like, yeah, kind of just add on that, it's really hard to like generate like that neutral data. Pretty
Yeah.
much. It's always gonna encode those biases pretty
Yeah,
much.
that's a very good point. Haven't heard about this. This is subliminal.
Yeah, subliminal learning.
Yeah, and then especially, when we move to large language models, and even now with this, pre-trained word embeddings, we are working with a really large scale of millions of texts. And if you want that scale, it's really hard to figure out what's going on in that data. I have co-authored the first paper that tried to look into what's in the pre-trained data. And we have struggled, I think this was maybe like 2020, to even put all the data on the available disk space. And then you need all these techniques to kind of understand what's in the data. So I definitely recommend taking data mining, like working with large collections of text is super helpful. And then so many things can cause trouble. So for example, at that time when we were pre-training models, people were aware of these biases and consequential harm. So they were thinking, how about we add a list of words, they called it naughty words, and we discard all texts that mention these words. And then our model will not have a chance to learn some of these associations. And then we have mentioned or analyzed and seen that in those list of words that researcher included something that's definitely not a harmful word, like queer, but they knew, oh, if I delete all the queer text from my pre-trained data, then my model won't have a chance to say something evil about queer people. And that resulted in deleting everything from the web that mentioned queer people, including the text from queer people themselves, which are obviously not, mentioning anything bad, they are informing other people. So you're causing this weird harm by you're trying to remove something that might cause harm, but removing everything about certain identity and demographics and ethnicity can also cause harm because now people can't learn anything about them. So it's a really, really challenging problem. Yeah.
And in computer vision, currently use some data augmentation techniques that rotating the JSON getting home data. So instead of removing text, can we just add more samples and try to noise, create noise in the
I think
like
the motivation behind that idea is good. I think the issue is covering those bases, right? Because there are so many identities, so many cultures, so many ethnicities in the world. And you will see now we are going to move to this pre-training data for language models that are massive and they are designed to be multilingual and whatnot. So now you have taken care of so many things and I think globally it's really hard to achieve that, but even within, let's say one country like the US, just take a religion as an example, it can be really hard to cover everything because different people they have different values and how do you reconcile, right? So again, I think adding more is better than removing stuff, but I think you will still run into issue that you can't cover everything in the world. And that for a while, I think was a big issue because people have, I think, focused a lot on gender, for example, because I think it was easier to study. And then there are all these other, societal biases that people just didn't, manage to look into. So we have like disproportionate attention to certain kinds of problems. Okay, so basically this is what I wanted to say about word embeddings. I do want to just go back and remind you why did we create these word embeddings. They are going to produce us embedding matrix. Remember a matrix where each row is an embedding of a word with a certain index in the vocab. So this is embedding of a word with the vocab index equal 0. So it's going to be of the size of the vocab times dimensionality of our embeddings. Once we have created it, we are going to make that embedding matrix our first layer in our classification model. And then for every input, which is a tokenized sentence, we are going to do a lookup operation where we are, each one of these words has an index in the vocab. And using their index, we can retrieve the corresponding row from the embedding matrix, and then we average these embeddings, and that's going to be our feature representation, which we will then non-linearly transform once or twice, how many times we want, and then have logits, softmax, and argmax operation. I also want to say that whether you treat these embeddings as part of your weights in your classification model or not is up to you. The reason why people keep them fixed very often is because this is a lot of parameters, right? So if I have a size of vocab of 30,000, and if I have 300 dimensional vectors, that's a lot of additional parameters to train. So more often than not, we keep this metric fixed, and then we learn only the other weights of neural network responsible for nonlinear transformations. And then before word embeddings, pre-trained one word thing, people did randomly initialize them. But I don't know any task where randomly initialize instead of pre-trained word embeddings would be a better option, unless your domain is so different than the data where the word embeddings are trained. But honestly, even then, there are just some structural properties shared across many domains that I think would be helpful. Okay. So now I want to shift gears dramatically. Let's maybe take 2-3 minutes break, and then we're gonna come back just to have also physical sense of changing the topic.
Do you have a favorite paper that sort of talks about what we think these models should be doing? Because that's the whole thing that I've been thinking about while you're running through all the ethical parameters. It's like, okay, this data is biased. but we have to use data.
Yeah.
So like, what should we do? Because, I don't know.
Yeah, it's just to be sure, I understand, is your question like, what are people want LLMs and other technologies to be doing for them? Like, what are the needs?
Yeah.
Or more like, how people want this issue and tension between utility and biases to be reconciled? Or maybe
I guess both,
yeah. Okay, let me write this down. Listen, I always have papers I want to share, so.
Yeah.
So papers for utility, like needs, and reconciling biases. Yeah,
I guess like even if the main goal is AGI, like there's something missing there.
yeah. I mean, I want to say that the end goal in everyone's mind is AGI. It is the most, sellable thing because it's vague and there is no way to deliver because you don't know what you're delivering anyway, right? So I want to say AGI is general, what everyone wants out of this technology. If anything, I think more people want, they have, you might be a clinician, or you might be a lawyer, or you might be a fact checker. You are domain expert, and you have a sense of what would be amazing to automatize. So people, or we say delegate. Yeah, share. I have a paper on delegation, and very often people want to delegate things that are boring, right? No one wants to do on stuff they hate to do. Something that's repetitive, intellectually not interesting, doesn't require any creativity. So there is actually a study a while back that was done in UK, and they asked people like, what do you want AI? Like, what do you want AI for? What do you don't want AI for?
Yeah.
And the huge number of people said they don't want AI for arts.
Okay.
And then because it was easy to find a lot of arts on the web, this is what we automatize, right? Like, I mean, I'm not saying we automatize arts, but we have automatized some easy way to represent images that can be deemed as art. So there is also a mismatch between what the general public wants out of this and what is real. Yeah. And I think I will correct you, it's not what AI researchers want, it's more like what AI researchers can do. Because what was easy was to scrape the web, including the entirety of GitHub and lots of art sites.
Yeah.
That was easy. No one was like, oh, we think this is the best thing to do, right? Like it's just what was easy, what was feasible, and this is what happened, right? As a result. So very often AI researchers don't start from a needs finding studies and then go from there.
That's interesting.
Which is honestly, I grapple with this a lot because I'm part of that space myself and what to do, right? Because it has led to some progress, but it's also very disruptive. Yeah, I guess my summary would be it's really messy.
Yeah. I should have used paper. I should have cited that question about what the.
Yeah, I will share some in Piazza.
Yeah, that'd be great.
Yeah.
Right, thanks.
Yeah, you got it. Okay, so as I said, we are going to now shift gears. Just to recap what we have done in the course so far is basically we have looked into supervised machine learning, and we have focused on the text classification task. As a reminder, I want to first say that text classification is a big task in NLP. It can serve many of applications, many of which you have mentioned yourself. And if we would to approach it with supervised machine learning, so far we have learned we learned there are 4 components. I think something that maybe isn't super extensively covered in other machine learning or deep learning class and was the most NLP-ish content of this course so far is how to represent text, right? So we learned that first of all, we can't just try to have, first of all, I said we need to work with numerical representations, right? Computers understand numbers, not words. And then I said, instead of having a single number for the entirety of sentence, we need more numbers to capture a bunch of features that are relevant for text. And I said we can't be too ambitious and try to find this kind of numerical vector representation for every single sentence by not splitting it into smaller chunks. I said we should first split it and then learn the representations of those chunks and then combine them. And that's exactly what we have been doing. So we have always been tokenizing the sentence. We have been using a word tokenizer, which is not great. And even worse, we have been using only white space tokenizer. White space tokenizer is terrible for languages that don't have clearly separated words like Chinese. It is not even good for English because it doesn't separate conjunctions, punctuation, and so on. And later we are going to learn better tokenizers, and we are going to move from this notion of words to something called subwords. In any case, once we have tokenized, our tokens so far were words. We learned with embedding for each one of these words. And for bag of engrams, we were looking at the counts and presence of engrams, and we were focusing on bag of words mostly. So once we had this feature representation, then we were defining a function that can classify that feature representation. We have learned about binary logistic regression. Then we moved to feed-forward neural networks, which are basically combining hidden transformations with nonlinear transformations with logistic regression in the end. And in both cases, we have been finding appropriate parameters of weights of those models by defining negative log likelihood. And then we were looking for weights that minimize it. So one thing in practicum that I asked you in the end was, how do we know whether a set of weights is better than the other? And here you should have remembered that our whole goal was to find weights that will minimize the loss, the negative log likelihood. So if I have two sets of weights, the one that give me smaller negative log likelihood are going to be better weights, right? And to find those weights, we have used an iterative algorithm called mini-batch gradient descent, which changes the weights iteratively by following the direction of the steepest descent, which is given by the gradient. So now I'm going to go over a bunch of things that are not super satisfactory with things we have learned so far, which will motivate some additional developments. And we are going to move away from this classification stuff into what we call generation. So instead of classifying a given piece of text, we are going to now focus on producing text. Okay, so first thing we don't like and kind of we talked about at the beginning of this class was that token order is disregarded in our current, let's call it state-of-the-art approach in this class. So if I have these two sentences, it wasn't terrible. In fact, it was great. And if I say it wasn't great, in fact, it was terrible, which have completely opposite meaning. Because we are averaging their word embeddings, we would end up with the exact same representation. Another issue is that when we have very, very long text, like legal contract, we want the model to be able to capture, even if I now have given you some way to preserve the order of words, I want the model to be able to connect what happened in the beginning to what happened at the end. Think about summarization of a book, right? There are characters that will be introduced at the beginning, and very often they are characters that appear at the end of the book. And you want to track what happened to this entity from the beginning to the end. And the book is really long, right? So you need the capacity to model what we call long-range dependencies. You need to know what happened at the beginning and what happened at the end, and not forget things in between. And both of these things we are going to try to address with our new neural architecture called transformer architecture. I'm going to say it. It's going to be a huge jump from feed-forward neural networks. to a transformer. Transformer is much more complicated neural architecture. After we come from the fall break, we are going to go into every single detail of the transformer architecture. So you will have a chance to learn it. And actually, you will implement a smaller version of it in your third assignment. But I do want to acknowledge that, if this was a deep learning course, there would be some progression from feed-forward neural network to transformer. So we are taking a big leap here. Another thing I don't like is that every single one of our word embedding is, and before I say that, so I told you that one word, the same surface form of that word can have different sense, different meanings, depending on the sentence it appeared in. How many embeddings will I have for word basing once I'm done training my word-to-vec mod? One, right? I will have only one. But here I'm showing you 5 different senses. So that's dissatisfactory, right? Although I know this word has multiple meanings, I have only a single embedding for it. And this is something we are going to again change with our transformer architecture, which will have a mechanism called self-attention, which will give us representations that are contextualized, meaning embedding of my word after many layers of transformation is now going to be changed from that static word embedding, which is kind of lexical, into something that takes into account other words that appear in the context, in the entire context, from the beginning to the end of the sentence. So we are going to move away from what we call static embeddings, which never change based on what other words appear in the context, to contextualized embeddings. As I mentioned a few times already, white space tokenizer, boo-hoo, really bad. So we are going to change it in 2 major ways. First way we are going to reapproach tokenization is to move away from these words being token into smaller units, which are going to be called subunits. So token will now be not only a full word, but it can be something like suffix, like ing. And maybe even more interesting to you, the way we have learned these embeddings from data, we're also going to learn the tokenizer from data. So again, I will have a large collection of written text. And instead of me deciding what the token should be and deciding which tokens go into the vocabulary, I'm going to use an algorithm called byte pair encoding, BPE. And I'm going to apply to my collection of texts. And this algorithm is going to learn what should be tokens and which tokens to put in the vocabulary. And also it's going to learn so-called merge rules, with which we will be able to tokenize our texts into tokens from the vocabulary that BPE itself had produced. So I find it really intriguing, maybe, if I have never seen NLP before, that now we learn word embeddings from data. We are going to learn our tokenizer from data. You see the trend is little manual intervention as we can possibly induce, which is to some people maybe not satisfactory because we have linguists. So why wouldn't linguists define what the token should be, right? But again, it's all about generalization to unseen instances. And once we start to define rules and features, it becomes really hard to generalize them to many cases, as many as, let's say, ChatGPT can handle. Another issue we want to fix is that, and I haven't talked about this too much, but your loss functions that we have been working with so far are not convex. Can someone remind me why then that's an issue? Yeah.
It's stuck in local member style ones.
Yeah, so convex functions have one global minimum, and you just descend, and you come to it, right? With non-convex functions, you have something like these two cases, right? So you might be descending and then you're stuck in a local minimum, or you get stuck in SAT. So we want to start in a better place in this loss landscape, which means that instead of starting from randomly initialized weights for our new transformer architecture that I haven't introduced, we are going to start from pre-trained weights. Specifically, we are going to again use a large collection of written text. These days, we literally use the entire scrape of the internet, whatever its latest snapshot is. And at a time when we didn't do pre-training all the time, we have to decide what we are going to use as our training objective that will help us learn useful features of language, but at the same time won't require that we hire any people to annotate any of this data. Because if we would need annotators, then we can't have the scale of the data. Reminder, again, I'm talking about terabytes of tokens for training these models. So two options presented itself. In 2017, 2018, we have used so-called masked language modeling, where you randomly drop a certain number of tokens in your input, and you try to predict which tokens you have omitted. And another one, which is more tied to latest language models, such as ChatGPT, is language modeling, which is the task of predicting what is the next token. And in both of these cases, because you have that text, and you either omit or you truncate the text, it doesn't matter, you know which word appeared, and you know which word is gonna appear. So you don't need to label this, and you can frame the classification task out of it. Or I should say with language modeling generation task. So by doing this, for a very long time, like think months given the scale, you get what we call a pre-trained model, where instead of some random weights, you have weights that are already capturing some useful features of language, because they needed to learn those features to be able to predict which word could follow the given text, or what is the word that was dropped here. Once you have that, you do your standard supervised machine learning, where you have your labeled data, and then instead of starting from randomly initialized weights, you start from these weights you have learned, and you continue training them. So effectively, for your supervised machine learning, nothing has changed. Instead of when you write your code and you write model.load or pre-train load, whatever you use, you are not going to load some random weights, random numbers. You're going to load the numbers that you have learned through pre-training. Okay, so this is how we are going to, through this pre-training, get into that better space in our loss landscape. And we are going to transfer all those useful features. And de facto today, we never start from randomly initialized weights. We always start from pre-trained ones, because they already capture so many useful aspects of language, both syntax and semantics. Okay. All right. So in this last minute, I want to now emphasize that I'm going to move away from what we call discriminative machine learning, which we use to classify things. So we have labeled data, and we are trying to learn the relationship between the features of our inputs and the labels. Now we are going to move to generative machine learning, where our goal is to generate new data that is similar to data it was trained on. So in the context of NLP, we want to create a model that's capable of producing more texts, right? So that's the object we are working with in NLP. That's our data. And we are going to try to develop a model a language model that's capable of doing that. This all that we are going to talk next is going to put us more or less into this timeline between 2017 and 2023. So we are approaching more recent time. Next time, I'm going to introduce a very, very, very old NLP task called language modeling, which is part of large language models, right? So language modeling as a task has been around for a very long time. We are going to talk a little bit about what it is, how we have modeled it between neural networks. Then we are going to see how we would do it with neural networks, talk about how we would extend that for something like machine translation, where you have both source and target text. So we are going to use something like called sequence to sequence models. And then we are going to see how to sample from the distributions and so on. And we are going to build towards transformer, which I plan to teach you about when we come after the fall break. And then once we learn transformer, then we are very quickly going to see what large language models are. Okay, yeah, see you on Wednesday.